Often in computer science, you're presented with a problem and you ask yourself, does there exist an algorithm to solve this problem? More generally, in mathematics and computer science, one often says things like, there exists one object with the particular property P. So in this segment, we're going to introduce a quantifier that takes care of these kind of sentences. Namely, there exists one value of x in the universe such that P of x is true. And this quantifier is the existential quantifier, shown here in red. So this proposition is read, there exists x such that P of x. Notice how this quantifier also has a scope, which I indicated here with the red parentheses. Now they are not needed here because the expression over which the quantifier applies is a single atomic proposition. But in general, don't forget to indicate the scope of the quantifier, where it starts and where it ends. Now the question is, where is this, or when is this expression true? There exists x, P of x. By definition, this expression is true if and only if P of x is true for at least one element in the universe. So that's very different from the universal quantifier, which was true for all x, P of x was true if and only if P of x is true for every element in the universe. Here, it's true if at least one element makes P true. Now, as we did before, let's assume for the sake of simplicity that the universe is finite. That is, it's made up of a finite number of elements, namely x1, x2, xn. Now, in this case, the expression or proposition, there exists x, P of x, is equivalent to the following proposition. Namely, notice that for this proposition to be true, there must exist at least one value in the universe for which P of x is true. So this value is either x1 or x2 or xn. So in other words, if this proposition is true, it must be the case that either P of x1 is true, or P of x2 is true, or etc., or P of xn is true. And that is the reason why these two propositions are logically equivalent. Now, what happens if we negate an existentially quantified proposition? Not there exists x, P of x. What is that equivalent to? Well, again, intuitively, if it is not the case that there exists x for which P of x is true, that means that P must be false for every single element in the universe, including x1, x2, and xn. In other words, P must be false for x1, and P must be false for x2, etc., and P must be false for xn. So in conclusion, the negation of this existentially quantified proposition is logically equivalent to this conjunction of negatives. Now, like we did in the previous segment for universal quantification, you should realize that this logical equality does not hold. In other words, to negate an existentially quantified proposition is not as easy as just moving the negation from the outside to the predicate inside of the expression. Now, like we did with the universal quantifier, we can always apply any quantifier to an arbitrarily complex proposition. It doesn't have to be a single predicate like P of x. So let's consider the quote-unquote proposition D of x and B of x, which is a compound proposition. Now, it's not really a proposition because, as you remember, the value of x is left unspecified. So let's fix that by adding an existential quantification in front of that expression. And by doing so, we actually specify a value for x here and here, assuming the scope of the quantifier starts here and goes all the way to the end. So to make sure that's the case, don't forget to add the parentheses around the scope of the quantifier. So this is now a proposition that you read as there exists x such that d of x and b of x. Now let's try to interpret this proposition of predicate logic back into English. For that we need to define a meaning for the predicates d and b. So let's say the universe of discourse for x is the set of all animals. And let's say that d of x stands for x is a dog and b of x stands for x is black. Then the meaning of this proposition would be there exists at least one animal that is both a dog and that is black. So a nicer way to say this in English is some dogs are black. And in general, every time you have an expression of the form there exists x, d of x, and b of x, a standard way to express that in English is to say some d's are b's, where d and b are the predicates or the verb phrases in the sentence. Now the question is, how do we represent this kind of expression with the same graphical representation we use for the universal quantification? So if this sentence is true, then we must first represent the universe for x. Again, let's do that with a red rectangle containing all of the possible values for x. And then let's draw a circle or set for the predicate d. Now, how are we to draw the circle or the set for b? Well, according to this proposition, it must be the case that one of the elements of b is also in d. In other words, the intersection between the sets b and d cannot be empty. Here is one way of drawing that. Here is the intersection of b and d where this element belongs to both. And that is the most general way of drawing the pictorial representation for this proposition. Notice in particular, it would have been wrong to draw the circle b completely inside the circle for d, as we did for the other example in the previous segment. Because what that would have meant was that everything that's black is also a dog. But that is not part of the meaning of this proposition. So in general, it is possible for a black animal to be something other than a dog, like this one. It is of course possible for a dog to be a different color from black. And again, in general, there are animals that are neither dogs nor black. So when you draw these diagrams to represent the meaning of these propositions, make sure to be as general as possible.